Generalizing learning with errors.
Well, generalizing is probably a very a failure of a title, because we obviously didn't do it. So I'm gonna start by telling the story of how this all came about. So the other author is Leonardi. He's the one with beard. And we had this seminar, like a student seminar in our grad school, and we call it the therapy group, because it's when we go and we talk about our problems, and we just want to tell everybody that what we're working on, and make sure that we're not crazy, and everybody's like, yeah, you seem fine. Okay. Because when you're a grad student and you do research, you look like the baby trying to paint an egg. It doesn't look very good. So at some point, I was very interested in this paper by Regev that introduces LWE. And if you know anything about that paper, is that it's a little bit complicated. It probably take you more than one sitting to finish it and understand it. So I gave a talk about it. I told them like outline what was it about, and my other two friends that are in crypto, they looked at me and said like, what are you talking about? I don't understand any of this. And the thing is, they are doing isogenies. They're in another realm. So when I show them this, they said, okay, you take a linear combination, and it approximates this B, and then you put a bunch of samples, and it looks like that. And they give me a face of what is that? That looks like very linear algebra, and where are the elliptic curves? So I was like, well, I don't know. There's no elliptic curves in here. And then I tried to tell them, no, you can actually make a symmetric key encryption with this. And it's very easy. If you assume that this distribution is uniform, then you just put the message in the second coordinate, and it's like you're masking it, right? And when you, in decrypting it is very simple. You just need like operations modulo P, and everything is straightforward. You don't need all this addition and elliptic curves. So why do you need all this complicated mathematics? It's very simple. And they were still not convinced. So I was explaining them how to construct a public encryption scheme. They said, what you do is you publish encryptions of 0, and then if they look like uniform, then a subset sum of them also looks like uniform. And it is also encryption of 0, and then you just add something at the end, and the decryption follows it exactly the same as in the symmetric case. And then I showed them this graph, and they were like, okay, you lost me. I don't want to see this anymore. But I think this is the graph that kind of is the most important, well, not the most important, but is the most important argument why LWE is important for cryptographers. Because it's very related to a lot of lattice problems like SVP, gap SVP, SIS, bounded static decoding, USVP. So this is in a survey paper by Larhoven. So I really like this one. And then I started talking about like there's this problem with LWE that with the LWE in the way that the community is using it, because they say, Regev proves that it's just as hard as a very hard problem in lattices. But it turns out that if you actually follow the reduction and you want to assume, okay, if I use an LWE solver to solve the SVP problem, then you turn out that you will need a lot more operations using the the LWE solver than using the current state-of-the-art SVP solver. So the reduction is not saying anything about the hardness of LWE. Or more like it's not covering the parameters that people is using right now. And if you analyze the reduction, most of the hardness goes into the average case to worst case. So there's probably something to doing here, which I don't know. So reducing from decision LWE to SVP. Not search LWE to SVP, then search LWE to decision, and then this is average case to worst case. It's a lot. That's what takes most of the complexity. But anyway, so then one day my supervisor told me, hey, there's this new paper about doing entry over these primes, what's it called? The Mersenne primes. He said, you should read the paper. And then I was walking the street and said, like, oh, what can we do just LW over Mersenne primes? What's so wrong about it? And then that evolved into doing LW over ZP. Then that seemed like something that someone should have thought about it. So I said, like, okay, let's not think about it. It sounds too dumb. Let's probably think about like a group. Why don't we do LWE over like a black box group, like a generic group, in the same way that people did this Diffie-Hellman and DSA over elliptic curves. Like that generalization, that step, improved the complexity, the hardness of and the efficiency of the primitives. So I was thinking about it and said, like, okay, so how do you go about doing that? Okay, well, let's try to think about LWE as a learning problem now, because it's learning with error. So there should be a learning problem in there. So if you fix the key, then this mapping, this is the first coordinate of your LWE distribution. This mapping sends the first coordinate to another is kind of the image of a homomorphism when you fix the key. And then you add an error. So okay, so you can see LWE as just image, like an element in the group, and this image that is a little bit modified. Okay, that sounds nice. So we'll see, like LWE then says, given a bunch of elements in the group, and this is a modified image under a certain hidden homomorphism that we don't know. So this phi of S is just an inner product with A, and this E is small, but we know what small means in ZQ. It's just elements that are close to 0. So why don't we do the same over a group? Okay, so how will that look over a group? So you say, okay, you have a group element, and here you have a homomorphism that is secret, and then you just corrupt it by an error. And okay, let's just do LHN. So we'll call that a learning homomorphism with noise. With this, phi is a homomorphism from G to H, and this E comes from a noise distribution, right? And then the problem is to output the phi. But here, you can probably see that if you're thinking of abstract groups, then what is this error? What does it mean to be small in a group? It's like what is a small reflection? That sounds a little bit funny. How do you output a function? Like in LWE, you just output the vector to which you're.
I don't know, but how do you even learn the homomorphism without writing it down?
Sorry?
How do you learn the homomorphism without writing it down?
without trying it out. So
Ideally, you don't, right?
yeah, that's where I'm going. It's like the problem is that you don't know how to output a function. It's like how do you say, okay, this is the function. In LWE, you output this secret vector in isogenies. So if you remember yesterday's talk, you output the generating elements of the kernel, but that doesn't sound like very generalizable. Like what do these two have in common? And then how do you mix these things? It's like in LWE, you take subset sums of them, but in an abstract group, you just if they're not commutative, then you just can take words. And how do you take words? And well, there's just so many things that look wrong with this. So it's like, okay, let's just tackle one by one and see if we can do it. So okay, here I'm repeating the same. And another example is in polynomials. The way you output a polynomial is by outputting the coefficients of them. So our proposed solution was for learning a function is that you cannot play a game. You say, I'm not going to output the function. I'm just going to say when an algorithm learns a function, and that sounds like a solution that is very well known for cryptographers. It's like if you win this game, then you're good to go. So what is the game? It's like, okay, if you take a bunch of elements of the public key, like or samples of G, and then this must have an E here. So samples, like LW samples, and then the challenger tells you, okay, now evaluate the function in this random G, and I'm going to challenge you. And they say like, oh, okay, this is the evaluation. And the learner has black box access to G and H. Right? It's going to win if it actually outputs the exact evaluation. So, okay, that seemed to work, and actually you can probably see how if you have an algorithm that learns learning with errors, then an algorithm that outputs the learning with errors secret, then you can learn a function. So this kind of generalizes learning, solving learning with errors, or solving the isogeny problem, or even solving this polynomial problem. So it seemed okay. What are the other challenges? Okay, we have to see like, what is the noise? What is this noise distribution? And in LWE, at least you want it to be efficiently sampleable, because if you want to add a noise, but you don't know how to add a noise, then it doesn't help too much the case of generalizing LWE, right? So in the traditional version, that you have a Gaussian distribution, but in the general version, we don't know. We also need that the error will be erasable at the end. So once you know the private key, you have to be able to erase it somehow. So for LWE, what you do is once you have a ciphertext, then you subtract the action of the private key on the first coordinate, and then you have the message like a little bit modified, and then what you do is you round it. So you rescale it and round it, and then you're good to go. And that helps to not only erase the errors when the message is binary, but you can erase the errors for every in every message space. So we need these two properties. So what's the first candidate? Well, okay, let's not add in any errors, and then let's see, because that solves these two problems if you don't add any errors. So in the noiseless case, then okay, we have actually an example. The conjugacy search problem, or is kind of an LWE or learning. It's a learning problem, in general. So because the conjugating is a homomorphism. It's an automorphism of a group. So that seems to work in certain cases. Now, a small noise, yeah, we have some examples, and we know it. It is learning with errors, renal learning with errors, and then this new integer learning with errors, learning with rounding. Those are all use a small noise, but they have a notion of a smallness in their groups. And then we didn't have any other idea so far. How do you satisfy these two properties? Okay, let's work with distances first. So let's see what can we do with this distance. So what distances do we have in a generic group? So, okay, we have the Hamming norm. That sounds a little bit dumb because it's like everybody is at the same distance from everybody else except for from itself. So it doesn't look very promising. They say, okay, what distance do they use in LWE that we can actually generalize it to any group? So in LWE, they use this called Cayley distance. So if you see this as an element of the numbers, the integers mod 7, then the distance from the 0 to 3 is just what's the shortest path in this graph. So how do they look in other groups? Like this in the dihedral group, they look something like this, where the generator set is a reflection and a rotation. So say, okay, then we do have distances in general groups. The problem is that computing these distances is hard in general, because you have to find the shortest word that expresses one element. So okay, so that defeats the purpose of LWE and of defeats one of the requirements. And then we have more problems, is that we don't know how to erase the error. How do we decode once we have something like this, and then we erase, we get rid of the action of the homomorphism, secret homomorphism on the first coordinate. How do you erase the error? It's kind of solving a bounded distance decoding on a general problem. That doesn't sound very promising. And even more, if you have non-commutative groups and then you want to mix them in the same way that we did it in LWE, then these error terms get kind of mixed in between of the others. So they don't go to one side. That sounds kind of annoying. So our first solution is okay, let's use abelian groups and let's see how it goes. But that sounds, if you map the abelian groups, we have a theorem that says these abelian groups look very similar to products of set P's, right? And you actually have a quantum efficient homomorphism from one to the other. So it's like we're returning back to LWE, kind of. And then, okay, the second solution is, well, take the error terms on the center, and so that will probably take them all to the one side. But this has another problem, that if anybody can compute the center, because the groups are public, then you just mod out, and then you end up with no noise, which defeats the purpose of adding noise. So far we're a little bit lost, and all this happened in these weekly meetings where we didn't know what to do, but my other friends were like, okay, well, you just probably can switch to isogenes and your life will be better. No, and I kept resisting. And then I had this idea one day, say okay, if you have these words, words of group and then error, probably you can just mod out by a secret group, and that gets rid of all the errors, and then you're good to go. Whoa, that sounds okay. And then you can actually, so this is different from the other one, because in the other one the center was public, because the group is public. But here you're meant to keep the group secret. And you can actually construct a public key crypto system out of something like this.
Sorry, quick question about
yeah.
that. So the group used to be public, right? Because you needed, or the center used to be public because you needed to sample the noise from that center.
Yes.
So how are you getting around that?
Oh,
that
but
problem?
the thing is, it is the decrypting party the one that samples the noise, because it's the one that computes the public key.
Oh, gotcha. Okay.
Yeah. And so you don't need to publish the secret. All right. So now, then how do you construct this? It's like, okay, the secret key will be 2 homomorphisms, and the public key will be similar samples, like a group element, and then the evaluation on the first homomorphism, and then this H1, and the H1s are taken from the kernel of the second homomorphism. Because being a normal subgroup and being the kernel of a homomorphism is the same thing. So, and then how you encrypt a message, you just take, well, here you take a word from them. How do you take a word? Well, we don't know yet, but you just take a word and on the first on the elements in the public key, and to decrypt, what you do is you apply the second homomorphism first to get rid of the errors. So then that will take care of this part. And boom, they're away. And then you apply the first homomorphism to the first coordinate, and get rid of of this part, like this. Boom. And then you have something that encodes the message. You still need to solve some sort of discrete logarithm problem here. But I mean, you can probably say, like, well, let's take a group where the discrete logarithm problem is solvable, and then you're good to go. Yay! But now, how do you find examples from where all this construction makes any sense? But anyway, so we're very excited. So like, okay, let's find all of the properties that it has. It's unbounded homomorphic, because if you multiply two encryptions of things, then assuming that this kind of parameter is in the center, then it goes all the way to to one side, and the multiplication looks like an encryption of the addition of the two elements. It potentially has a very large message space. So it's not only binary, but it will potentially have a lot. And that's because if it's as big as on the order of this tau, that is a parameter of the protocol. And you recover it by just using the discrete log. And it has potentially small keys. And that's because in LWE, you need to increase the dimension, because you have an abelian group. So if you have an abelian group, then you have just a very limited possibility of combinations of this, of the public key. But in a non-abelian case, even two elements will just give you a potentially unbounded number of combinations, because it's all of the possible words. So it will potentially have small keys depending on how you encode this group elements. So it looks fine. But then we have to overcome certain challenges, like the number of normal subgroups in this H has to be large enough so that it's not dumb. So that you can just like brute force all the normal subgroups. And the number of homomorphisms from G to H has to be large enough. Then you have to be feasible. The outputting a homomorphism from G to H has to be easy, because if you don't have any way to generate a random homomorphism from G to H, then what's the point? The normal subgroups have to be easy to generate. And even more, like all these probability distributions have to kind of decide that they're non-zero only in this normal subgroup. So you have to kind of solve some sort of decisional, what is this kind of subgroup belonging problem or something like that? So it looks like nothing will probably satisfy all these properties, but then we thought about, why don't we just take polynomials, and it's like learning with, like learning with errors. You just multiply by a polynomial, but instead of adding a small noise, you add some noise that you can erase by evaluating in an element, in a secret element. And so that looked very nice. So the noise subgroup will be just all of the multiples of this x minus alpha. This B had to be restricted somehow, but it looked okay. And then the LWE samples look like this. So at that moment, it's like, oh, this looks so nice, because it's like you have kind of unbounded homomorphic just for free. And why hadn't anybody thought about this before? So I told my supervisor, and then his words were like, if your construction works, then it's a shame for all the crypto community. So like, that smells funny. So then I went to tell my friends, okay, help me break this, because it somehow has to not work. But then they had this. Say, why don't we just talk about elliptic curves? Sounds good. Why don't we instantiate our problem with elliptic curves? Because an elliptic curve is as generic as it gets. So let's just take, and besides like keeping a secret kernel of something, is supposed to be kind of the special thing of the isogeny problem, right? And so everything that you need to know about elliptic curves, if you just forgot the isogeny talk about yesterday, is that elliptic curves are groups. They're more than groups, but that's all we need for now. The isogenies are group isomorphisms, and given the right circumstances, it is hard to compute an isogeny between two elliptic curves, assuming that it exists. And the isogenies are like almost determined by the kernel, like up to elliptic curve isomorphism. And so how will the protocol look like with using elliptic curves? Oops, sorry.
You're too far back, I think.
There you go.
Start again.
Start again, because I can spoil the end.
That's
Speed
cool.
reader.
Okay, there you go. Sorry about that. So it will look like a kind of a short sequence of two homomorphisms, two isogenies from one curve to the other, and we have that these isogenies are easy to generate, and that is easy to sample from the kernel of an isogeny, because you just take a linear combination of the generators. And so the samples will look like an isogeny elliptic curve point, and then another elliptic curve point in this one. So they will look very, very short, because it's just two elliptic curve points. Well, now you have to kind of polish a bunch of them, but it seemed okay. So why hadn't anybody thought about it before? So it keeps smelling funny. It's like, probably something's wrong about this. But then one day, as we sat with Chris, and we had a security proof. And it was very complicated. We have to, we were proving that this new supersingular isogeny lermite with errors is distribution looks like uniform. Then we have this decision to search reduction, and then this a security reduction from the security of the crypto system to the decision version. So it looked very good. But of course, that's no. Sorry about
That's good because we missed the beginning, right?
Yeah, so that was not the case. Because once we sat down and said, okay, let's write down the proof, we look like this. Not very happy fellows. Because not only we didn't have a proof, but we had an attack. So we constructed and broke our own crypto system. That didn't look very publishable.
Until this conference.
Until this conference. And so in the attack was kind of, it was rather simple. So that's why we were, because initially it seemed like if you base the security of your crypto system on kind of, so you have functions and you have samples and you have secret kernels, it looks a lot like the hidden subgroup problem. So we always thought about, there must be some connection to the hidden subgroup problem. But it was myself that I didn't want to believe on that, but even though in the back of my mind it's like, yeah, probably there is. But I didn't want to believe because our two constructions were very nice. And the attack is kind of reducing it to, is through Shor's algorithm, which is solving a hidden subgroup problem on abelian groups. And it was rather simple. So if you have in the public key less elements than the rank of the group, then you can just find out what are the coefficients that you use to mix them, just by solving the multi-dimensional discrete log. So that sounds something that we should have figured out from the beginning. So what happens when you have more than the rank? When you have more than the rank, then you can generate a lot of elements in the kernel of the second homomorphism. And at least for isogenies, if you reveal a lot of elements in the kernel, then you're doomed, because you know what the kernel is, and you know what the isogeny is. So that defeats the purpose of adding errors. So we're very sad. So it's like, well, in the general case, are we overlooking something this trivial? Because it seemed like a very, very, very trivial attack. What are we overlooking? And then you start questioning. Does it make sense? Why is it a bad idea? Somebody tell me, please. Why is it all pointless? And then on the quest of trying non-abelian examples, and so okay, let's just try matrices or something. But it seems that the matrices have very few interesting normal subgroups. Then back in my undergrad, I studied Coxeter groups, and it seems that a problem very similar to this was actually already solved. It doesn't look very promising. And then the break group, and then after the walnut using grades, nobody wants to look at my proposal. Then there's another paper using Burnside groups that we haven't been able to find out what are the normal subgroups of this thing. They say, okay, some group that has all of the subgroups are normal, and so they're all classified, and they all look like this, and they all look very unpromising. So what we wish for is creating this super singular isogeny learning with errors. It will look very nice, but we failed. And we failed to establish a connection with another problem with HSP, except on the case that the connection is fatal. And we failed at finding nice non-abelian subgroups. So far we don't have any good ideas for that. And well, there's some positive outcomes of this, and I think is that we understood that we need to understand more about LWE. We understood that if we want to go through the algebraic path, then let's use non-abelian groups. We need to find examples and probably a possible connection with HSP, because HSP and non-abelian groups, it seems to be still a good case for the construction. And if we want to go to the geometric path, saying that, okay, take the small elements, then we have to use abelian groups. But for that, if we want to follow the reduction of regular phi, then say like, okay, what does it mean to have a Gaussian distribution on an abelian group? It looks still very complicated. And in general, there's still things like, okay, suppose that we have a good candidate for our groups, how do we construct abstract versions of some of the primitives? Like if FHE, this or IBE constructed based on LWE, probably can we construct it based on this abstract version of LWE? Can we use probably rings instead of groups? Probably we actually need the multiplicative structure. Can we have some general, there's several ways to generalize SIS. Which one is the one that makes more sense? And well, I like to end with this with this line, arguing that why do we need to still understand more about LWE? It says that lemma 3.7 on the Regge, lemma 3.7 on Regge paper, for instance, would be utterly shocking if an algorithm solving decision LWE for error rate beta could not somehow not naturally differentiate between LWE with error rate beta over 2 and uniform, except on the obvious case that it knows the answer but it hates you. And that's the end. Thank you.
Questions?
I'm still a bit puzzled. So you're breaking your own scheme by a quantum attack using Shor.
Yes.
But even in a pre-quantum world, this would be quite an astonishing result. And so, do you have any tech in a pre-quantum world which doesn't need Shor as a subroutine?
No. We still think that we're probably overlooking something, because in using polynomials, then you can actually break also the scheme without using Shors, because you just use solve GCD problem in there. But in the elliptic curve case, I don't have any.
If you can construct a group, a non-abelian group with lots of normal subgroups, can you do what you want to do?
If we know how to like kind of produce those subgroups, because
Okay,
it's
so
not
you'd be able to compute subgroups.
to compute subgroups, to say like, okay, these are the classification, and you can produce them with this algorithm in a kind of random manner.
Because the subgroups are part of the secret key?
Yeah, they're part of the secret key.
Could the same thing work with like a non-commutative ring with lots of alleles?
That's a good question. And we've been thinking. Well, I've been thinking about that for a bit. But it seems that.
Yeah.
Mm,
Because they're easier to construct, but I don't know, maybe it doesn't work, but.
Well, if it works, it can go to Eurocrypt next year, and if it doesn't, it can go to the next CFAIL. So I think you guys should talk.
the thing is, in the ring, so if it's not commutative, you're using the multiplicative structure that is not commutative. But at some point,
Oh, of course,
you need
the group, yeah.
you need to kind of invert the action of the homomorphism
Yeah.
somehow. So if you don't have inverses, then yeah.
You're right.
So
The
it's-
addition is still commutative, so then you have the same problem as before.
So what's the minimum length of a paper for CFAIL?
No minimum.
Can we just
But
drop
it does
that?
have to be in Cypher.
Submission deadline is passed.
Yeah.
Failed.